All right. And it's like slow motion up here today. We're in day 7. Everyone has the notes? Chapter 11, section 8. Anyone not have chapter 12 notes? Chapter 12, they're on the back table over there if you need them. All right, we're talking today about the end of chapter 11. We're going to do what's called Lagrange multipliers. And it's Lagrange. There's another mathematician, or you'll hear in like different engineering courses, Legendre. They're kind of spelled similar, so don't confuse the two. This is a method that was developed for helping us find maximum and minimum values like we were before, right? We were finding max min, but this is used when we're trying to take a function and find a max or min of it on some constraint, some restriction of its domain. And so this method is the one we employ. So we already learned in 11.7 that we can find the local max and mins and saddles of a function on its implied domain. How do we do that? How do we do number 1 here? How would you find the local max and min saddle points of a function on its implied domain? You compute that D thing, right? So you have to find the critical points, and then you compute D if D is greater than la 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 la. That's how you do it. Now, number 2, we know how to find the absolute max and min of a function on a closed bounded region, and that's the one where we would first compute the same thing we did for D to look on the inside of it, and then we had to move around the boundaries and figure out what's happening on the boundaries. So those are the 2 methods. Now we have this new method that we can use whenever we are going to restrict our function or subject it to some what we call constraint. And here's the method. Now, the method that we're going to start with is the Lagrange multiplier method when we have 2 variables. 2 variables means that we have a function f of x, y. So that's a surface, right? And we are going to subject it to a constraint, g of x, y equals k. Now, first thing I'm going to do is I'm going to show you the formulas and show you the actual technique of what we're going to do, and then I'm going to try and explain it geometrically. It's a tough sell, but I'm going to try and do it. All right, so here's what we got. If we have a function and we constrain that function by this equation, this is an equation, then to find the max and min values of f, you have to do this. First, find all values of x, y, and lambda. Lambda is going to be a constant that we're going to have to figure out what it is, such that what? The gradient of f, what's the gradient of f? It's a vector, right? That vector is the partial, since it's 2-dimensional, either partial with respect to x, partial with respect to y, right? That gradient has to be equal to lambda times the gradient of g. In other words, the gradients are what? Scalar multiples, which means they're parallel, right? So we have to figure out where the gradients are parallel, and then we also have to make sure that the constraint equation is satisfied also. Then what we do once we find those points is we evaluate our function at all the points we found in this thing here, and then the largest is the max and the smallest is the min. If we can do that, we will have found the max and min. Now, shall I try and explain why this works? Try and give you a little visual? Do my best. Where are you? There you are. Okay. Let's start first. This is our constraint. Our constraint was g of xy, right? Equals k. G of xy equals k. G of xy by itself is a surface, isn't it? Yes? G of xy? So there's g of xy. Now what I'd like to do is I would like to make g of xy equal to a constant. Making it equal to a constant, doesn't that find like a level curve on that? Y'all see that level curve? Let me pull g out a little bit. Can y'all see that? So if I take that surface and I restrict it to a constant, I'm just talking about this particular ring on G, on the surface. Got it? Now, what I'd like to do is I'd like to talk about the gradient, or look at the gradient. The gradient of G is a vector that is perpendicular to the curve, isn't it? Gradient's always perpendicular to your tangent. So if I look at this, see my gradient there? See how it looks like it's perpendicular to that curve? Yes? Okay, so that's my gradient of G. Now, I also have down here, in two-dimensional space, the same picture, looking straight down, okay? So you can see the gradient vector runs perpendicular or orthogonal to the curve itself. Everyone understand that? Okay. Now, I'm going to take my G and kind of bring it out of here because I don't want us to get that confused with F. Now, F is the function I'm trying to find the max and min of, right? So now let me put F in here. So F is some other surface. Notice that that ring does not hit my function, right? It's not there. In fact, what I think I'll do is I'll take the gradient out. I want it. No. Thought I could take it out of there. That's what I want. Okay. So what I'm doing is I'm getting that ring that was up there out, and I'm just transposing it down to the XY plane, just so we still see it in our picture, right? Now, what I'm supposed to do is take my original surface and constrain it to that circle, which means I want to take just the points in that circle and map them up into this function, which would mean I get that blue curve. Do you all see that that blue curve is what you get when you take all those circle points and throw them up into the, what? What? Oh, that's the thing I was talking about a couple weeks ago. I don't know. We can, yeah. Well, let me ask you this. Do you see that that circle, if you plug it into the function, you get that blue curve up there, right? So the blue curve is F restricted to, well, constrained to our G equation, right? Here's our G equation. Restrict our function just there, map those up there, you get that blue curve. And what we want to know is what's the highest and lowest point on that blue curve. So let me pull F completely out of here. So now we have this, right? And then show you, do y'all see those points pop in there? Right there, there. Do y'all see them? They're gone. They're there. Yes. I pulled F in here for a second. Do y'all remember level curves? All the level curves of function. Back in the very beginning, we said if we want to draw a surface, we can draw the level curves and then get an idea what it looks like. So look at all those level curves of this function. And what I would like to do is show you a top view of those level curves. So if I take this and I turn it like this and look straight down, then I'm looking like that. Do y'all see that? Now the green right here is my constraint curve. There's the gradient of G, right? That's the gradient of G. And these blue rings are the level curves of my function, F. The red vectors, what are these red vectors? These red vectors are the gradients on these level curves. Okay, so if you go to to this level curve right here, and you look, that's the gradient sticking out. So it's just a bunch of the gradients of the level curves. Now there's more I need to throw in here. Now I'm going to actually put the gradient of f in the picture. So if you're on this blue curve, and if you're on the blue curve at some point and you compute the gradient, you get this blue vector. All right? Look at it from the top and check this shit out, okay? There it is from the top. All right, you see it? All right? I need this to be side by side. Let me make this, there we go. Okay, so check this, what's going to happen here. Is the gradient of G parallel to the gradient of F right now? They're not parallel. But watch what happens if I start moving around here. Now, go back. Now they're parallel. And where am I on my surface over here? I'm at that maximum point, right? I'm at that highest point. The highest point is occurring where the gradient of both of them are parallel. Y'all see that? That's geometrically, I'm trying to convince you that it works. Now, if I move around, can't go too far, I went too far. Looks like they're parallel there again, right? And then take the level curves off of F. Where am I now on F? I can't even see it. Where the hell am I? Well, there it was, backside. Okay, we're on that backside. You see that? And that's where they're parallel. And again, now I'm at a minimum. So that's just a visual verification that the Lagrange method works. Just visually showing you that when those two gradients come together, you've got to be on the highest or lowest point of that curve. Pretty cool, huh? Where are my computer science majors? There's your code for that. Wow, I spent some time on that, mother. Jeez. I had too much time one day, I guess. Too much free time. All right. Here we go. So let's apply it, right? It's time to do an example because seeing it visually is one thing. Oh, wait, hold on. I still have more to talk about. All right. When we say that we wanted to figure out where the gradients are parallel, right? Gradient of F is equal to lambda gradient of G, then it really means this, right? Just distribute the lambda through. And now, two vectors are only equal if their components are equal, so we can set the components equal to each other, which is this, isn't it? So in order for us to figure out the max-mins, where they happen, we'll have to be able to solve this equation, or we'll write this equation out, we'll write this equation out. That gives us two equations. And then the constraint equation is a third equation. And so we're going to have three variables, x, y, and lambda, and we're going to have three equations, and we're going to try and solve that. Three equations, three unknowns. The trick is that the equations are not necessarily linear equations. If they were linear equations, we could use Gaussian elimination, systems of equations stuff to solve it. But because they're nonlinear, we're going to have to do it some other way. That's going to be the challenge. So here is our first example. We have a surface, right? Find the maximum and minimums of f of x, y equals x squared plus 2y squared on x squared plus y squared equals 1. What is x squared plus y squared equals 1? That's a circle, right? So x squared plus y squared by itself is a what? Like that. If we were to look at that, it would just be like a cylinder, right? But we're fixing the radius at 1. That's going to be that's basically going to be what's on the ground. Okay, so remember how we took G and we looked at it down on the ground? That's G on the ground. Now take those points, throw them up into the surface, you get this, right? And we want to know what those points right there are. Where do those happen? Where are those highest and lowest points occurring? All right, let's set it up. So F is, in this case, F of xy is x squared plus 2y squared. Now, g of xy equals k. That's this equation, x squared plus y squared equals 1. Agreed? So then what's g of xy? It's the left side, right? This? That's the part we're going to call g of xy. So g of xy is x squared plus y squared. So what I want is the gradient of f to be equal to lambda times the gradient of g. What is the gradient of f? 2x, 4y. Times lambda, what's the gradient of g? 2x, 2y. That means 2x, 4y has to be equal to 2 lambda x or 2x lambda, doesn't matter which way you do it. Anyone have an opinion as to why they use lambda? I've never thought about it, actually, until right now when I just asked you. I don't know why they use lambda, but maybe it's because it's Lagrange. Maybe they use it because it's Lagrange's method. Yeah, I know. So, okay, well, it is what it is. So now let's, remember I said what this is going to come down to is 3 equations, right? 3 equations, 3 unknowns. I'm ready to set up my 3 equations. Now, everyone has their own way of doing this. You know, this is the way I do it. You don't have to follow my way. But I always like to write down my 3 equations. My first equation is that 2x must equal 2 lambda x. Now that I'm getting from the first components have to be equal, right? These two have to match. The second equation is what? 4y equals 2 lambda y. Man, I'm so pumped up. I'm getting a delivery today. Sorry, I just remembered this. I'm like a gadget person. Anybody here like a gadget person? So my wife and my neighbor, they're going swimming, so I'm turning on the pump to my pool right now. So I'm excited because I'm getting a shipment today. It's a new relay that I can control. It's an 8 relays that you connect to your network, and then you can control them. And I have them hooked up to all these different other relays that trip other things. So I can move the valves on the pool so I can make it go from like the water comes out over here or it comes out at the slide. You know, all these different things. Or I can turn these speakers on outside. It's pretty cool. It's pretty fun. That's the type of shit that I like. So I'm excited. Excited about later on today. I get to hook all that up. Okay, so I'm doing this. I thought y'all were solving the equations already. What's my third equation? What's my third equation? It's the constraint equation. So your last equation will always be that last one right here. All right, so how do you figure we solve this? I need to figure out what x, y, and lambda are that satisfy all 3 of these at the same time. Now, I'm asking you this because I saw some things that I was concerned about on the test when it came to solving equations. Like, look at this first equation right here. Should I divide by x? No, right? I should instead do what? If I want to get x by itself over there, what should I do? Just move everything to one side and factor or do something like that. But don't ever divide by a variable that you don't have control over, right? Like I would never want to divide by y here because I don't know, maybe y is 0, right? Can't divide by 0. So instead we move things over. So what I'm going to do, I'm just mess with this first equation over here. I'm going to take, how about divide everything by 2? Can I do that? Yes, okay. X, why don't I bring that lambda x to the other side? At this point, can I factor an x out? And I get 1 minus lambda equals 0. And then don't you just set each of those to 0? X is 0 and what? Lambda is 1. So let's think about what this means, all right? So far, to satisfy the first equation, one of those two things has to happen, right? And to get a solution, we have to satisfy all three at the same time, yes? So what I'd like to do now is use that information. I'm not even going to mess with the other ones yet. I'm going to use that and now say to myself, all right, what did I say that stood for? An S with the little line there at the end. Suppose? No, I thought I told you all that before. Okay, so I'm going to say, look, this is what makes my first equation true, right? One of those. So let's suppose that x is 0. Let's just suppose that happens. Now, let's look at the other ones. Oh, you know, I forgot to label my equations. Let's call that equation 1. Let's call that equation 2. Let's call that equation 3. All right, so if x is 0, does that help me with anything over here? Which equation does it help me with? Equation 3, right? So if x is 0, then that would imply equation 3 would imply that y squared must be 1, right? Or negative 1, right? So that means that y equals 1 or y equals negative 1. Y'all still there? But now I have to look at both of those scenarios, right? So what if y is 1? So now within this suppose, I have a new suppose. So now suppose that y is 1. What does that give me? Go back up. Up here in the second equation, if y is 1, lambda, you could solve for lambda, couldn't you? So suppose y is 1, then equation 2 tells me that y was 1? That lambda is 2. Do you all follow that? This is very important, and it's one of the hardest things for me to grade on test is logical process here, right? We looked at the first equation. We said, okay, it could be two things, right? We looked at one scenario. When we looked at that one scenario, it created two new scenarios. We looked at one of those scenarios, and it gave us an answer for lambda. So right now, I have an x, right? Well, sorry, I have an x, I have a y, and I have a lambda that make all three true. Agreed? They're not the only ones. Because what I haven't done yet is looked at y is negative 1, right? And I also have to go back and look at lambda as 1. So I have to look at all these different cases. Do you see that? Okay, so now what I'd like to do is underneath this, I'll just put x, y, lambda, then must be what? X was 0, y was 1, and lambda was 2. So that's kind of its own little thought there. And now let me suppose what? Y is negative 1. If y is negative 1, what does equation 2 give me? Still the same thing, isn't it? Lambda is 2. But that gives me a whole new ordered triple, doesn't it? It gives me 0, -1, 2. That was all under the assumption that x was 0. Shall I move on? Okay. Are we done with this problem? No. Now I need to suppose what? Lambda's 1. It's a great question. That's one of the hardest things in these problems is when are you done? You can be done as soon as you've exhausted these two, because no matter what else happens here, right? No matter what else happens here, the only way this first equation is ever true is if these two things happen. And you have to satisfy them all, don't you? So you have to satisfy this one. You're not going to be able to come up with something over here that works without x being 0 or lambda being 1, right? Does that make sense? Okay. So as soon as we exhaust lambda's 1, we'll be done. So how does lambda 1 help me? Right here, doesn't it? Lambda's 1, I can go in here. So y would have to be 0. So if lambda is 1, then equation 2 tells me that 4y equals 2y. Yeah, and don't divide by, right? Don't divide by y. You subtract 2y on both sides, you get 2y is 0, and then your only possible answer is 0. What does that tell you? If y is 0, equation 3 tells you what? X squared must be 1, which means x must be 1 or -1. And guess what? You have to look at both of them, right? So do we have a triple here? Do we have a triple? Well, we have lambda's 1, right? We have y. Because of that, y has to be 0. And because of that, we could have an x be two different things, right? Do I need to go and look at what happens if x is 1 and -1? No, because I already know what lambda and y are, right? I already know what they are. So all I needed was x, and I found out that x could be one of two things. So now I have two answers from this part. They are that I could have x is 1, y is 0, lambda is 1, or I could have x is -1, y is 0, and lambda is 1. And now that gives me a total of 4 points. Now be careful. This is not x, y, z, is it? It's x, y, lambda. So to figure out the maximum and minimums, all we're really going to focus our attention on are the x's and y's. And we're going to take those x, y's and plug those x, y's where? Into where? Way up back into the function, right? All this work was just to tell us where potentially would you have these maxes and mins. Where do they occur? They occur when the gradients are parallel. Where are the gradients parallel? At those x and y values that we just found. Okay, go back up there and plug in those values for x and y, and you should get your max min. So we have f of xy equals x squared plus 2y squared. And we need to find, first of all, let me go f of 0, 1. Then we have to go f of 0, -1. We have to do f of 1, 0. We have to do f of -1, 0. F of 0, 1 is 2. F of 0, -1 is still 2. F of 1, 0 is 1. F of -1, 0 is still 1. So these are ordered triples, right? 0, 1, 2. 0, -1, 2. 1, 1, 1, -1, 0. Wait, did I just say 1, 1, 1? I did. 1, 0, 1, -1, 0, 1. So what is the maximum value of that function on that constraint? What's the maximum value? 2. Minimum value? 1. Where do they happen? Well, you can tell, right? And doesn't that kind of match up to the geometry of this? We had 2 places where we were the highest, right? And if we look at it from the top, where does it look like those happen? Well, where do they happen for us? It was at 0, 1, right? So this must be our y-axis. Isn't it? That's our y-axis. Okay, hope that made sense. Any questions? Yes. Yeah, it doesn't matter. Yep. The only use of lambda is that we have 3 equations. Oh shit. 3 equations and 3 unknowns, right? If lambda wasn't around, we'd have 2 unknowns and 3 equations, which would mean that we have a problem. It helps us lock it into one place. So once we get it, we won't use it for anything. All right, next thing. Although you could say that lambda is the scalar multiple, like we said the 2 gradients are parallel. That's the scalar, right? That's the scalar is the proper word to use, but you know what I mean? It's like how do they differ? Oh, well, in this case, in one of the cases they were twice as much. It was twice as long, a factor, All right, so now let's take a look at this problem here. This problem is very similar to the one we just did. Okay? But what you're going to see now is how this Lagrange method is really going to help us do larger problems. Find the maximum and minimums of this function on this disk. So instead of having equality right there, right? This right here, instead of having equality, I have inequality, which means that I'm not looking at just the circle, the ring. I'm looking at everything inside of it too, right? So if I look at this domain on the ground, it's everything on this little disk down there, right? I want to take everything on that entire disk and map it up into the function. You're no longer going to get that blue curve, right? You're going to get that entire region right there, right? Everything. Well, that's kind of hard to see on your screen, but you'll see it though? I'm going to take that surface completely out, but it's this thing instead. Yes? And I want to know the highest and lowest values. Any ideas? Any ideas? Ideas? That's not any easier to see, is it? I thought by making it yellow it would be a little easier to see. Do you see where we have a difference? Are the maxes going to be the same? Yeah, the maximum points are still the same, aren't they? These are the 2 highest points. But what about the minimum? They used to be this point, right? The one on the backside? But now the minimum is the bottom, isn't it? Because we have to consider the inside of it too. So, any ideas? What if I don't restrict it? What if I don't restrict it at all? Could you find that lowest point? How would you do that? Do the D thing, right? Compute D. Remember, we used D to find like local max, local min saddles, and that's how we also used it in the previous class when we had it like on a triangle and we need to look at the inside part of it. We would use that same idea that we had with D. That's what we're going to do here. We already know how to figure it out for the boundary, right? For the boundary, we use Lagrange. For the inside, we just go use the partial derivative stuff that we did earlier from 11.7. Understand? Well, I'll work through it so that you see. I'm not going to work through the whole thing. I'm just going to get that one part. So we have f of x, y is x squared plus 2y squared. This time we're on x squared plus y squared less than or equal to 1. So what I'd like to do is I'd like to first consider the part in here first, right? Let's look at that. I'll work with the boundary and I'll use Lagrange for that. So in there, what I'm going to do is try and figure out if I have a local max or min in there. So how did we do that? Well, we got the partials, right? Partial with respect to x, partial with respect to y. Partial with respect to x is 2x. Partial with respect to y is 4y. And then what we did is we set those both equal to 0, didn't we? So when is a partial with respect to x equal to 0? Well, that happens when 2x is 0. That happens when x is 0. Partial with respect to y equals 0 happens when 4y equals 0, which means y is 0. So that means 0, 0 could be a local max or local min, couldn't it? Now, we do not have to calculate D. We don't. Because, why don't we need D? Exactly. And then compare that to what we get with Lagrange, right? And then that's it. It's just a comparison. So we don't actually have to go through and now to say, oh, this is the highest or lowest. That's what the D does, right? Local max, local min, or saddle. We don't need that information because if we just plug 0, 0 in, we'll know the value and we can compare it to everything on the boundary. Okay, so now the rest of it would be computing it. Let's compute f of 0, 0. And that's obviously just 0, right? So that is one potential thing to look at. And then the rest, we actually do the boundary now. And for that, we do the Lagrange. Right? It doesn't matter which one. Yeah. Either way. And so, see previous note. And what did we get from the previous example? We got those 4 things, right? Or actually these right here. That's what we got. So if we take those now, oh, yeah, that'll work. And compare those. The only thing now is we have this one to consider too, right? And now you see we have a minimum that's not these, right? The minimum is actually going to come from that one. So our max would be here, right? These would be our max points, and then this one right here would be our min, and we're done. Questions? Find the maximum minimum of 4x plus 6y with the constraint x squared plus y squared equals 13. So I'll show you the picture of it first. 4x plus 6y is a plane. That's z equals 4x plus 6y, so that's a plane. X squared plus y squared equals 13 is a domain, it's a circle, right, on the ground. If we take those points on the ground and we plug those into that surface, we get this weird tilted looking ellipse thing on the plane, right? And we want to know where the highest and lowest points are. So we should have one highest and one lowest, right? Now, do we need to consider the inside? No, because that constraint equation was an actual equation. So I just have to do Lagrange here, nothing else. Lagrange. All right. I don't want to push too hard, but can I go straight to the three equations? Okay, what would equation 1 be? Four equals 2x lambda, or 2 lambda x, doesn't matter. 6 equals 2y lambda. And the last equation, x squared plus y squared is 16, or 13. Now, if you need to remember where those are coming from, this is basically partial of f with respect to x equals lambda partial of g with respect to x. This one is partial f with respect to y equals lambda times g with respect to y. This one is g of xy equals k. All right, that's what I just did. All right, where do you want to begin? How about I just do a little bit of cleaning up on this first one? How about 2 equals x lambda? This one over here, how about 3 equals y lambda? I haven't done anything crazy there, have I? Okay. Now what? See, in the last problem, weren't we able to move stuff to one side and then factor? And then we were able to say, oh, set that and that is 0, and then we got equations, right? X is 0, lambda is 1. Here, please don't tell me x must be 2 or lambda 2 here, right? You're not going to say that? Right? X must be 2 or lambda must be 2? No? I only say that because I've seen it before. I just want to make sure you're not going to do that. You could solve for lambda in the first two. I agree. You could solve for lambda, yes. I'll do it just to. Now, if we do that, we are going to divide by x, right? So we have to pay attention to that if we do. We can do it. We just have to pay attention to it. So if I solve for lambda, I would have lambda is 2 over x, wouldn't I? And I would have to say I would need to make sure I'm very clear x can't be 0 here, all right? I need to make sure I am clear on that lambda can only be 2 over x if x isn't 0. So if you go through all this work and somehow come up with at the end x is 0, you're going to contradict yourself. Do you see that? Okay. I'm only doing that because it was suggested, so what now? You do the same for the other one? Solve for lambda on the other one? Yeah, okay. I have no problem with that. So if I solve for lambda on this one, I get 3 over y, and I need to also say y can't be 0, right? What now? You want to set them equal to each other? Right? If lambda has to be this, and lambda has to be this, then they have to be equal to each other. So from that, we could say that 2x must equal 3 over y, and I'm going to put here, as long as x and y are both not 0. I'm going to keep track of this condition that I have the whole way through because I want to be very careful with my algebra. Pardon me? X could be 2 and y could be 3, but there's an infinite number of things that x and y could be here. What we have is a relationship between the two. You're giving an example of one particular answer, but you wouldn't have enough time in the day to go and figure out what they all are, right? So how about this? You could go 2y equals 3x. Do you all agree with that? Solve for y or x. Let me solve for y because I like y more than x. So that's 3 halves x. So that's our relationship, right? Y must be 3 halves x. Everyone follow? Now what? If you go into the third equation, in case you forgot or in case it's not on the page, like in my case, I'm going to write it down. That third equation says x squared plus y squared must be 13. So I can rewrite that as x squared plus y, but y we said was 3/2 x, and then squared must be 13. And now what we have is an equation with just x in it. So this becomes x squared plus 9/4 x squared must be 13. I'm sorry? Oh, combine. I didn't hear what you said. Yes, you could combine them. What would you get? 13/4 x squared equals 13. Multiply both sides by 4/3 or 4/13, reciprocal, both sides. X squared is 4, which means x is plus or minus 2. Well, I'll write it this way. X must be 2 or x must be negative 2. Any questions on the logic that we've followed so far? I mean, in the big scheme of things, the calculus in this problem is already done, isn't it? I mean, like the calculus is just that the gradients are parallel. That's the result of Lagrange. The rest of this is algebra. It's solving a system of nonlinear equations. That's what it comes down to. So now, if x is 2, do we know what y is? Oh, yeah, remember up here, we said y is this. So if x is 2, what's y? 3. So from back up there, I can say y is 3. If x is negative 2, then what's y? Negative 3, right? And then lambda. I don't necessarily need lambda, but what did we say? Lambda was 2 over x, or lambda was 3 over y. So what's 2 over x? In this case over here, what's 2 over x? 1, so lambda is 1. Over here, what's 2 over x? Negative 1, so lambda is negative 1. Do you see that I found an x, a y, and a lambda that make everything work, right? Found x, y, and lambda that make everything work. Am I done? Yes? Plug those in and figure out what the function's value are? What the function's value is? Yes? No. No. And one more thing you have to look at. It would have given us the same thing, because 3 over 3 would have given us the 1. In fact, it better give us the same thing. 3 over negative 3 would have given us negative 1. Not necessarily a suppose, but we did assume something. X and y couldn't be 0, right? None of this works if x and y is 0. So we have to consider that now. We have to say, well, what if it was 0, right? Then we could have never done this. We could have never divided through, right? So now what I need to do is I need to take that into account and say, all right, separate from all this, suppose that x and y are both equal to 0. Well, would your first equation be true? No. So we're done. Right? If y is 0, is this equation true? No. And of course, if x and y are both 0, this equation. So x or y or both being 0, in any of the cases where x or y or both are 0, there's no way these equations are satisfied, right? So we chunk it. It's not possible. So I'll just put equation 1 becomes 4 equals 0, which is obviously a contradiction. 4 is not 0, so we're done. We can throw that out. Not a possibility. But we have to consider it, because just because it didn't happen in this problem doesn't mean that a problem down the road, when we do this, we actually get a new set of solutions. In fact, I think there is a problem either that I'll do in here, or a problem on your homework, or a problem on a quiz or something where that does have to be considered. So that's That's why I said the hardest part of this, grading this, is that I'm grading more than just the answer, right? It's not just multiple choice, here's your answer, fill in the circle. It's, did you look at all the possibilities? Did you consider the fact that you have to look at that zero division? Did you look at, if you broke it like in the previous problem, if you broke it into two supposes, or the previous, did you ever go back and look at lambda as one? Sometimes it won't affect your answer because you'll still get the right answer, but I need to see that you considered it. All right. Next. Just so y'all know, I'm expecting a student. Today I've been giving exams to my internet classes. They have to come in and take like a face-to-face exam. And all morning long I've had students showing up. I have a student who's supposed to be here between 2:30 and 3, and they're supposed to knock on that door. So when that happens, I'm going to stop, go out there, get them on a computer real quick. That'll be when we have our 5-minute break. All right, 10-minute break. Just want to give you a heads up. Hey, I showed all that work. Oh, wait, no, that's a different problem, isn't it? Yeah, we should work through this one. Well, yeah, I'm going to work through it. All the work is there on the page, I think. But it's more of a reference for you. All right, so we are trying to find, this is kind of a cool picture. Here's our function, e raised to the xy, which looks like this weird thing right here. And we're restricting it to this, which is not anything, it's not a circle, it's not anything that we're used to seeing. But I went ahead and graphed it for you. This is it right here. This is your x cubed plus y cubed is 16. That's what it looks like. So if I put that on the ground over here, do y'all see that on the ground over here? Take just those points and plug them into that function. I'll move the function up so you can see like that. Let me show you, map those points into the curve, and you can see that they come up the side of that little wall, right? And then they go back down. What'd you call it? What? Oh, plateau. Okay. So it goes up and then down. So we want to know where the max min points are. I think we would all agree we definitely have a max. Do we have a min? It doesn't look like it, but doesn't mean it's not there. We have to actually see if it is. Okay, function e to the xy, constraint x cubed plus y cubed equals 16. 3 equations. I'm going to start labeling them 1, 2, 3. Like that. All right, first equation. What's the partial of f with respect to x? Y e to the xy. That must equal lambda. What's the partial of g? Now, g is this guy right here, isn't it? Partial g with respect to x? 3x squared. All right, what's the second equation? Partial of f with respect to y? X e to the xy. Lambda, 3y squared. And then the last equation is the constraint itself. All right. Now, without looking at my solution, which I have worked out there on the next couple of pages, what tactic would you want to employ here? Solve for y for the first equation? Okay. Now, I agree with that because I agree we can do it because y is by itself. Well, oh wait, hold on. I don't know if I do agree with that. Because look, if you solve for y, isn't y still up here? So you would be solving for y, and then it would be in terms of itself, and that's kind of a circular thing. You can't really. You could solve for e to the xy because this one has an e to the xy right here. Are you kind of thinking then set them equal to each other later? You could do that. Could you solve them both for lambda and then set them equal to each other? Yes? Was that? Yeah. Now, if I do solve for lambda, I will have to make a condition, right? Because I'll be dividing through by something, a variable. So what do you want? I mean, I don't care. What did I do in here? Because I'll do something different than what I did here and see if we can get to the same place. Is that what I did? I solved them both for lambda. Okay, so I'm not going to do that because that's already worked out in your notes. So I don't want to do it that way. I want to try something else. So solve it for e to the xy on both. So I'm going to isolate this here. I'm going to isolate this and so the same in both, which means that I'm going to divide both sides here on the first equation. And I'm going to rewrite that. I don't like having that 3 like that. Divide both sides by y. Over here, e to the xy. I'm going to go 3 lambda y squared. I'm going to divide that by x. Now, I have my conditions there, right? My conditions here were x and y can't be 0. So y can't be 0 here. X can't be 0 here. Now set them equal to each other. I don't know if this is going to work. But you got to try, right? Now what? Oh, and I'll also put my condition here. X and y can't be 0. Yeah, you can multiply both sides, like both sides by x, both sides by y. You can do that, right? Because you're already assuming they're not 0, so you're not multiplying both sides by 0. So if you do that, it becomes 3 lambda what? X cubed equals 3 lambda y cubed, which is what? You want to take out the 3's, divide both sides by 3? Is that what you wanted? Okay. Now what? You could say x cubed is y cubed, but then you would have to make what assumption? You would have to get rid of lambda, so you'd have to divide by lambda on both sides, which means you would have to make the assumption lambda is not 0. You could do it. I'm just saying you'd have to say that. How about this? How about lambda x cubed minus lambda y cubed equals 0? Is that fair? Moving the lambda y cubed to the other side? Could you take out a lambda and be left with x cubed minus y cubed equals 0? Could you do that? What else? We know that lambda being 0, right, would make that true. And then we know that x cubed minus y cubed would make that true. All right, let me see. Right now, here's where we are. We know that lambda must be 0 or x cubed must equal y cubed. Do you agree with that? If x cubed is y cubed, what can you tell me about x and y? They're equal because you can take the cube root on both sides. You don't have to worry about plus or minus or anything on that, right? That means x must be y. How many supposes do we have here now? We kind of have 2, right? We have we're going to have to say, first, let's see what happens if lambda was 0. And then we're going to have to come back and say, what happens if x is y? What we're not saying is lambda is 0 and x is y. We have to look at them separately. So shall we start with lambda 0? So I'm continuing my work up here. I'll start in a different color now. Suppose lambda is 0. And I'm also going to add up here x and y can't be 0, because doesn't that all follow? I mean, all of this is a logical thought, right? Everything is following. X and y can't be 0. All this happens, and I get to lambda 0. So this is all my assumption right now. So if that's true, then do we get something ridiculous to happen, or what? Look at equation 1. What does equation 1 tell you? Y, because lambda is 0, right? So that means y e to the xy must be equal to 0, because the right side is 0 here, right? And e to anything can never be 0, right? So that means y would have to be 0. Is everyone clear that I can divide both sides by e to the xy, get it out of here? Because that's always a positive number. So don't have to worry about division by 0. So now I just get y is 0, but what's that? What's that? Contradiction. That's two arrows going into each other. Okay? So it's like I assumed this, right? I said, hey, look, everyone, x can't be 0, y can't be 0. And at the end I said y is 0. Wait a minute, you said it, y can't? No, I contradict myself. So I'm done. So basically what that tells me is that lambda can't be 0, right? That assumption is not going to make all these true. Y'all follow? So I can say that's not going to happen. So now my next supposition, is that a word? I think it is that x is y. Is supposition a word? It is, right? I just haven't used it in a long time. What if x is y? What can you look at? Equation 3. Equation 3 would tell you, you could do it two ways. You could do x cubed plus y cubed now becomes x cubed again, equals 16, which means 2x cubed is 16, which means x cubed is 8, which means x is 2. And if x is 2, what does that mean? Y is 2. And if x and y are 2, can you tell me what lambda is? Somewhere we should be able to get lambda, shouldn't we? You don't technically need to find lambda. If you get x and y, you should be okay, but we should verify that there is a lambda that's possible, because what if this contradicts something about lambda? So it's always good to find the actual lambda. It shouldn't be too hard. Let me grab the first equation. If I take the first equation, replace y with 2, e to the what? 4 equals the other side, which was 3 times x squared, so 3 times 12, so 12 lambda. So e to the 4 over 6 is lambda, which is a number, right? So lambda is e to the 4th over 6. Have I considered everything? Am I good to go? What's the deal here? What's that? Yeah, what about x, y being 0? What if x and y are 0? I'll do that one right here. Suppose x, y equals 0. Is the first equation okay if x and y are 0? Yes. Second equation okay if x and y are 0? Yes. Third? No. So it can't happen. Right? What if just x is 0? This one? What if just x is 0? Look at this one. Then y would have to be 0 also, right? which means that that can't happen. So you can't even let just one of them be 0. They both wind up having to be 0. Do you see all the subtleties of this? I mean, it's not as simple as just, oh, I got something, finally I'm there. You know, you have to consider everything. So this would mean that equation 3 would mean that 0 is 13. Oh, 13? 16. Not happening. All right. That's cool because I worked it on your notes. I worked it a different way. I solved for lambda on your notes and worked it out, and we get the same result. We didn't check the value, did we? F of 2 is what we'd want. If you plug 2 in, you should get e to the 4th. Now, this brings up another question, though. We only had 1 point, did we? And I'm trying to find the maximum or minimum value. Now, we know it's a maximum because of the picture, don't we? But what if we didn't have the picture? How do I know that's a maximum value? Why is it not the minimum? See what I'm saying? That's right. All we have to do is find some other point that satisfies our constraint, plug it into the function, and see if it's higher or lower. Back to the picture, what we're saying is, look, we found this point, right? It happens at 2, 2, and then it goes up e to the 4th. That's where it is. Well, if I can find another point that lives in the domain, in other words, another point that lives on this curve, and plug it in, I'll be somewhere on this black curve, won't I? If it's lower than, if it's a smaller value than what I just got, then I know that that had to have been a maximum. If the one I plug in is higher, then we know that that one has to be a minimum. So it's just a process of elimination. So this would not be enough just to say, okay, that's it. You have to now verify it's max. So can someone give me another point that lives on the constraint? How are you going to get another point on the constraint? How about this? Let x be 0. That means y cubed is 16. So y is the cube root of 16, right? So we have a point, 0 cube root of 16. That lives on our constraint, doesn't it? Plug that into the function, and what would you get? The original function. You would have to go e raised to the what? 0. E raised to 0? 1. And that is definitely smaller than e to the 4th. Follow my logic there? This is going to be equal to 1, which is smaller than e to the 4th. Therefore, f of 2 equals e to the 4th is going to correspond to a maximum value. Yes? Well, let me try and do it this way. What does 2? There's several ways of explaining this, but 2 cubed, right, is 8, right? 2 times 2 times 2. Okay, 2 to the second, 4. That's 2 times 2. 2 to the first is 2, right? 2 times 1. So what's happening is every time I come down by a power, right? What's happening to the result? It's getting cut in half every time it comes down, right? So when you get to 2 to the 0, you cut it in half, and it gives you that. And then if you go 2 to the negative 1, what happens? You cut 1 in half, so you get 1/2. And you go 2 to the negative 2, you cut 1/2 in half, and you get 1/4. And then you can keep on going, right? That's just to show it by a pattern. But then to show it another way would be, what's x squared over x squared? Well, as long as x isn't 0, that's 1, isn't it? But properties of exponents says that if you do x to the n over x to the m, it's x to the n minus m, which means that this would have to be x to the 2 minus 2, which would be x to the 0, which means that x to the 0 has to be 1. I mean, there's different approaches, but I hope that convinces you, I guess, enough. Okay. Because someone told me that's what it was. That's why it is. Yeah. 0 factorial is 1 by definition. We define it that way. That's different. It's not just like we define things certain ways, and that's how we define 0 factorial. There's no way to show it. That's the definition. So, what's next? Ooh. Let me just see if there's anything here. Can I skip this one? Yeah? Okay. Whoa, hey, easy there, easy. All right, so look, this one, the notes include the solution, okay? The gradients are here. That 1, 2, and 3 are the 3 equations. Solving 1 and 2 for lambda, we get this. Setting them equal to each other, we get x is y. We plug that into the third equation. We get an answer for x. That means that y has to be this. And then we go in and figure it out, all right? Now, great thing about Lagrange is that it can be extended out now to functions of 3 variables instead of 2. So now if you're trying to find the maximum of a function f of x, y, z, subject to a constraint g of x, y, z equals k, then you have to do the same thing. Gradient of f equals some scalar multiple of the gradient of g. It's going to be 4 equations, 4 unknowns. And then we'll have this. The second thing here is the constraint itself. Now we have to find all the points x, y, and z, and lambda, and get those, and then use the x, y, z to find max and min. All right, so there are the 4 equations you'll have. Partial of f with respect to x equals lambda g, partial, then the other partial, then the other partial, and then our 4th equation is constraint. We will have 4 equations, 4 unknowns. We are solving a system of nonlinear equations with 4 unknowns. 4 equations. As you might imagine, the algebra of this is going to maybe be a little bit harder. There's more to keep track of, that's all. Hold on. Maybe to help motivate this, let me go back, because we can do these examples, but let me go back to last class, which was a long time ago. Do you remember this disaster of a problem that we did? That one? Yeah? It was day 6. Whoa, shit. Where is it? Oh, right here. This one, the box. We came up with the volume function, and we did all this derivative junk, and then, oh man, it was just a nightmare. And then I kept on going and going and going and going and going, and finally we got to something. Do you remember that? I think you were all asleep at that point by the time I did that problem. But what I want to show you is how simple that problem is going to be for us today. Okay, so let's read through this real quick again. You want to find the volume of the largest rectangular box with edges parallel to the axes that can be inscribed in the ellipsoid. So the idea, again, was that we had this box, and inside that box, in the first octant, we had an x, a y, and a z coordinate that took us to that top corner. If we multiply that box by 8, we got the entire box inside of the ellipsoid. So the volume of that box was 8xyz. 8xyz. And then what we did is we solved for z, right? We solved for z, and we plugged it into that equation. Yes or no? Y'all are looking at me like, okay, freaking disaster. Now let's look at this. This can be pretty beautiful. All right. What is the thing that we're trying to find the maximum of here? The volume, right? The volume was 8xyz. But xyz couldn't just be whatever the hell we wanted it to be. It had to live in the ellipsoid, didn't it? So what was the equation of that ellipsoid? I don't think you have it in your notes, do you? No. It was on the notes up here. Let me go back. It was this one right here. That was the ellipsoid right there. Right? But look at that thing. Do y'all see what it is? It's an equation, right? Doesn't that constrain our x, y, and z? I mean, our x, y, z can't just be whatever it wants. Our x, y, z has to satisfy that constraint equation. That's our g of x, y, this time z, not x, y. We have three variables. That's our g of x, y, z equals k. Let's see if I can remember that. Let me see if I can remember that when I write that down. 9 plus 36y squared 4z squared. What was it, 36? Okay. That was our constraint, right? That's our g of now x, y, z, three variables, equals k. And my volume, can I just look at my volume over here? I'm going to scrap it out. I'm going to call it v of x, y, z. Our volume is like our f now, isn't it? Can I leave it as v, or you want me to switch it to f? You don't care? All right. How many equations should I get? 4. The first equation should be the gradient of what? V, and then equals, so what is the gradient of v with respect to x? I mean, not the gradient, the partial of v with respect to x. 8yz equals now the partial of g with respect to x times lambda. Lambda times 18x. Does anyone have a question on where that came from? No? Next one, equation 2. 8xz equals 72y with lambda in there. Next one, 8xy, lambda, 8z. The last one is the whole thing over there, right? All right, there it is. And now we have the pleasure of trying to figure out what x, y, and z make all those true. So, let's make this an in-class quiz. You can work together. Go for it. Find x, y, z, and lambda that make all four of those. Should I said 3? All 4 of those true. You'll turn in your own work, okay? So do this on separate paper. I think my student's out there throwing up because she's looking at what was up here and she's like, bleh. So I already explained how multiplying everything appropriately got 8xyz on all 3 of these equations. If you take the first 2 equations, you set them equal to each other, then you get this. If you move this to the other side, you get this. If you factor out an 18 lambda, you get this. Set 18 lambda to 0, you get lambda 0. Set x squared minus 4y squared equal to 0. Move it to the other side, take the square root, you have to do plus or minus. Right? Now, when we do this, we can start throwing out some of these things right away. What if lambda is 0? Let's just consider this for a second. If lambda is 0, what would that tell us? That right there would have to be 0, right? Which means that either y or z would have to be 0. which was a contradiction because whenever we multiplied by x, y, and z on these, we said they couldn't be 0. Also, if that lambda is 0, then x or z would have to be 0. So for the same argument, lambda can't be 0 for these. So I can throw that out completely. No. And then this second one, x is negative 2y. I can throw that out. Now the reason I can throw that out is because remember, the x and the y and the z are dimensions of this box. We're in the first octant, right? We're letting x grow, y grow, z grow to try and adjust it to get the maximum volume. If I let my x be negative 2y, then they're off by a sign, aren't they? Right? One is positive, one's negative. We don't want that. We want to be in the first octant. So just by the geometry of the problem, I can throw that out. So I just need to consider the x is 2y. Now the question is, what do you do with that? Well, let's see. Do I have something in here? X is 2y. Could I plug that in? I could plug it in here, right? I could plug it in here also. Couldn't I? What would happen if I plug it in right here? If x is 2y and I plug it in right here, I'll have an equation with what? Y and z in it. So what could I do with that? Solve it for z. Let's see. So I'm going to take x is 2y. I'm going to plug that into equation 3. And I'm going to plug it into equation 3 before I multiply through by y. No, what did I multiply through by? Z there. Only because I don't need it, okay? I don't need that extra z. I can go back to that equation. So what would that equation be if I plugged in x is 2y? What would we get? 16y squared equals lambda 8z, or 8 lambda z. Does that help at all? 2y equals lambda z. Does that help at all? What I was hoping for is that I could get, I know that x right here can be written as 2y, right? I was hoping to get z in terms of y also, so that I could get this whole equation in terms of y, and then I should be able to solve it. The problem is when I'm trying to get z in terms of y, what am I getting in here? A lambda also. That's a problem. So maybe that approach isn't the right approach. Any other suggestions? You want to solve 2 and 3? Like, you want to do 2 and 3 together, kind of like I did 1 and 2 together? To come up with, let's see what happens. If I set those together, so I'm kind of going right here, I'm just kind of like, shit. So I set these two together, 72 lambda y squared equals 8 lambda z squared, right? Do some manipulation, move things around here. Can I divide through by lambda? Technically, I have to be careful, but didn't I already eliminate lambda being 0 as even a possibility? So at this point, it's safe to say lambda can't be 0, so I can divide it out. If I do that, then divide by 8, I get what? 9 y squared equals, oh, wait, yeah, that's right. Z squared, which means that 3y equals z. Why am I not doing plus or minus? Because I already want the quadrant, right? Hey, now that, do you see that? No? Okay. So I want my y and my z coordinates to be positive, so I don't have to consider plus or minus. So I've got z is 3y. I've got x was 2y. And now I think I can go to equation 4, can't I? Equation 4 is I can replace x with 2y, so 2y squared, plus 36y squared, plus 4z squared, but z is 3y squared equals 36. And I think we're there, aren't we? I mean, this is going to do it. This should get us a y. Once we know what y is, we know what z is. Once we know it, and we'll also know what x is. So let's see here. What's this? 4y squared times 9, so 36y squared, plus another 36y squared, plus another 36y. No, is that right? Damn. Okay. Equals 36. I'm going to divide everything by 36. I don't. At this point, I really don't care what you do, right? This is going to give you 3y squared equals 1, and that means y squared is 1/3, which means we get plus or minus 1 over root 3. And you can ignore the minus because y isn't going to be negative, so y must be, that's bad math right there, hold on. Y must equal 1 over root 3. So if y is 1 over root 3, what is x? 2 over root 3. What is z? Three over root 3. Just using our equations that we got up here, right? Z was 3 times y. We said y was 1 over root 3, and x was 2 times y. So that should be it, right? I did what? Oh, is that what you're talking about? I had those upside down? Okay, thank you. How do we know this is max? You could test, right? You could pick another point that you know satisfies your constraint. But with a problem like this, geometrically, there's only a maximum, right? There's not a minimum. The minimum is nothing, no volume at all. So we're pretty much done. You could find what the volume is, but that's the actual. Now, if we go back to last class, I believe that we had that at the very end. We finally got to y equals 1 over root 3, and I just threw my hands up and said, at that point, you can find what x and y are, right? Or x and z, right? So what do you think? Do you think the way we did it today is a little easier or not? I mean, if you can solve it, right? So it still has some inherent difficulties in it, but I would argue that that's a lot easier because think of the derivative we needed in the previous class. The derivative with the square root, and we had to carry all that stuff. So much room for error, where these derivatives were pretty straightforward, right? I mean, this stuff should not be an issue to set gradients equal to each other. It should not be an issue. All right. And we need to be done with this section. Now, let me go back here. No, I'm in the wrong notes there. So let me just help you set up this problem without doing it, okay? I'm not going to go through the method, the Lagrange method to do it. But let's say we're trying to find the maximum volume of a rectangular box with no lid if it is to be made of 12 square meters of cardboard. Rectangular box, right? 12 meters of cardboard. 12 square meters of cardboard. So what I have is a rectangular box. It does not have a lid, right? Maximum volume. What's the volume of this box? Well, why don't we just label this side x and this side y and this side z, right? The volume would be x, y, z. What is the constraint? The fact that I can only use 12 square meters of cardboard, right? 12 square meters of cardboard is the surface area of the box. What is the surface area of this box? Well, it's the area of that front side, right? What's the area of that front side? XZ. What's the surface area of that back side? XZ. So I have 2XZs, don't I? I have 2XZ. All right. Then I have the side of the box, right? What's the area of that? YZ. And then I have the other side over here, which is also YZ. So I have 2YZ, don't I? Plus, then I have the bottom of the box, which you can't really see in my drawing, but it's there, right? The bottom of the box has an area of what? XY. And I don't have a top because they said it doesn't have a lid. So I just have one XY here, right? That must be equal to what? 12. Do you see your constraint? And do you see your objective? We call it the objective function. Do you see the two? There's your F. There's your G equals K. And now you go gradients, blah, 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 blah. Work it out. Understand? It would all work the same. If you swapped variables around, you wouldn't even have to use X, Y, Z. You could have used, RST. And then as long as your volume formula said RST and then everything else was set up right, it would work. What if it had a lid? 2XY. Would that change your answer? Absolutely. Right? Okay. Find the maximum volume of a rectangular box with double bottom if it is to be made of 81 square feet of cardboard. Same exact problem. It has a double bottom. Isn't that the same as having a bottom and a top? So it's the exact same setup as the previous problem, except this right here would be a what? 2, and this would be, what was it, 81? 81, that's it. I would, yeah. Yeah, I guess there's some, some things could get lost in translation there, but how about this one? Find the point on the sphere x squared plus y squared plus z squared equals 4, which is closest and farthest from 3, 1, negative 1. So look, there's a point sitting out there in space, right? You've got a sphere sitting out there in space. I want to know where the points are on the sphere that are closest to that point and furthest away. Closest and furthest away. Make sense geometrically? So let's see if you can set this one up. You're trying to find the points that are closest and furthest. So what is it that we're trying to find? What's our objective function? What's the thing we're trying to find the max and minimum of? The distance between the points, right? The way we want to look at it right now is we have a point sitting out there in space. That point is the point 3, 1, negative 1, right? Yes? Now, this is critical. What we want to look at is the other point is just some arbitrary point sitting out in three-dimensional space. It has an x, y, and z coordinate, right? I want to know the shortest distance between those points. And here comes my constraint. My constraint is what? That point's got to live on a sphere, you see? So start with the objective function first. Let's call it d for distance, right? The distance between 2 points, those 2 points in arbitrary space is what? 3 minus x, or you could say x minus 3 squared. You could do it either way, right? Plus y minus 1 squared plus z plus 1 squared. That's the distance between two arbitrary points. But now here comes your constraint. Your point must live on a sphere. So the x, y, and z that are up there have to now be constrained to this equation. X squared plus y squared plus z squared must equal what? 1? 4? 4. Okay. This is your, what's that right there? That's your constraint, right? That's your g of x, y, z. And then up there, that ugly thing, all of it, is your objective function. That's your f of x, y, z. Now, you may remember this from Calculus 1, that whenever you're trying to find minimum or maximum distances, you can actually find the minimum and maximum of the distance squared. So you can get rid of the square root and not have to worry about it with the derivative, or you just track it along with you. Because look at, what's your partial going to look like? It's going to be pretty ugly, isn't it? So what I'm saying is, what you can do is you can totally change this problem to d squared, and when you do that, work with this instead. I'm just say blah blah blah, and then call this little d. Little d is capital D squared. So what you're doing is you're saying, I'm going to try and figure out what maximizes and minimizes the square of the distance. Whatever does that will also maximize and minimize the distance before it was squared. That just, do you all understand? That gets rid of the root part. It's very common practice when we're trying to do optimization. So your derivatives will be much nicer. I would suggest you try and work through that problem. That's a good problem. And that does it for 11.8. Oh, well, you know what? Do y'all have this in your notes? 3 variables, 2 constraints? Maybe not? Yeah. Okay, if it's there, I'm not going to give you any problems like this ever, but I want you to all be aware of it. All right? If you have an objective function, f of x, y, z, you can actually come in, instead of constraining it to one thing, you could constrain it to 2 things. And then find the max mins. I'll give you a visual example. And that ain't going to do it. Okay, let's say we're trying to find that point 3. That was that point 3, 1, negative 1. We were trying to find the points on this sphere that were constraining, that made it furthest and closest, right? What if we said, instead of that point that we're looking for, furthest and closest to that point, instead of it living on this sphere, it lived on that sphere and its intersection with some plane. So where that plane would intersect that sphere would make some weird sort of like elliptical shape, right? So we have a plane equation, we have a sphere equation, and we have our point. Then this, where the plane cuts through the sphere, would create a curve, and we're looking for the point on that curve that would be furthest and closest from that one. So now we have 2 constraints. You'll see it, sphere's one, plane's the other. If you have that scenario, you can do Lagrange still, but what it requires is, instead of saying that your gradient of f has to be parallel to your gradient of g, it has to be parallel to the gradient of g plus parallel to the gradient of your other constraint function. So in other words, your vector has to be the sum of 2 other vectors. And u and v are scalars, with mu and v. Yeah, we're just adding a new function. Now, imagine what that does, though, to your equations, right? Because instead of setting the first partial of x equal to lambda g, you also have this plus mu h. And then you have this. And so it can become pretty complicated. So we have 5 equations. 5 equations and 5 unknowns. You have the first partial with respect to x, with respect to y, with respect to z. Then you have the constraint, first constraint, then you have the second constraint. So you're trying to figure out 5 different variables. X, y, z, lambda, mu. Have fun. So it can be done. Now what I did, because I didn't like that, is I just wrote a program to do it. So here's f of x with 1 constraint. And so I type in my objective function, I type in my constraint, I type in my constant, and I actually got Mathematica to go through and get all the solutions. So that's with 1. You can do a constraint, f of x, y, z, 1 constraint, or you can do f of x, y, z with 2 constraints. So let's do that one with the sphere and the point, okay? I want to see, I haven't seen my code run in a while. Let's see if we can get an answer. So we were trying to do the objective for, y'all want to do the square of the distance? X minus 3 squared plus y minus 1 squared plus z plus 1 squared. That was it, right? And then the constraint was the sphere, x squared plus y squared plus z squared. And I had that constraint, that constant was equal to 4, right? And then you click here, and hopefully I don't bring this to its knees. Let me try this, 4.0. That's not what I wanted. There it is. These are the points. X coordinate, y coordinate, z coordinate, and then L is lambda. Lambda, x coordinate, y coordinate, z coordinate. And then these are the actual distances. Now, this is the distance squared. This is the distance squared, so you'd have to take the square root of both to get the correct answer. Pretty cool, huh? Do you remember me talking to you about how as great as Wolfram Alpha is, it doesn't really give you the functionality. What I'm trying to do is convince people in here to get into coding up stuff, because I think it's a good skill. Where the hell's my code, man? Oh, there it is. Screw it. Let's go. We don't have time for that. Is it time to go? I know. Trust me. I want to go too, but we have to. I think we have to, as a class, kind of make a decision. My goal in Cal 3 is always to finish the book. I mean, because there's 2 more chapters, 12 and 13. So we kind of got to make a decision as a class. Are we shooting for finishing the book, or are we content with just, it's okay if I don't see it, I'll be okay, type thing? You know what I'm saying? Yeah. I mean, I'd like to keep pushing, even though I know it's hard sometimes to be here. We gotta keep the grind going. All right, chapter 12. Nobody needs the notes? No one needs notes for chapter 12? I guess I do. Where am I? I don't know where my notes went. All right, here we go. Double integrals. Chapter 12 is titled, I was going to say multiple integrals. Chapter 12, multiple integrals. All right, so we've spent a lot of time in Chapter 11 talking about differentiation, right? We had functions of several variables. We had the idea of surfaces. Then we came in with, we've got tangent vectors, directional derivatives, right? Partial derivatives. We could use this to find max, mins, right? I mean, that's a lot very much like we did in Cal 1. Talked about derivatives, max, min. And then after that, we started talking about integrals in calculus, right? Cal 2 is integration. So now what we're doing is instead of doing integrals in two-dimensional space, we're now going to go to three-dimensional space, four-dimensional space, etc. So we'll start with double integrals. In Cal 1, how many of you saw Riemann sums in Cal 1? Riemann sums? Okay, if you didn't see Riemann sums, it's okay, but Riemann sums, I think, are one of the most important things to see in Cal 2 or 1 because it gives you a visual idea of what's going on with integration. So, and it helps us build formulas. So you've seen this before, integral, right? A to b, f of x dx. What that meant geometrically was that we were going to take a function like this curve. We're going to look at it on an interval from, let's say, a here to b here. In this case, it's 0 to 5. And what we're going to do is approximate the area underneath it by cutting up a bunch of rectangles and then adding up their areas. And if we add them up, we get an estimated area, and the true area is here. So how do we get a better estimate? More rectangles, right? And the more we get in there, the less error there is. And to get the true area, what we did is we took a limit, right? Because limits let things go, either get real big or real small. So what we did is we said take the limit as the width of these rectangles goes to 0, which is the same as saying let there be an infinite number of rectangles. And then with that idea, when we take the limit as f of x delta x, now what was f of x delta x? Going back to our picture, if I looked, and I'm going to draw on top of my board here, if I look at the width of one of those rectangles as the change in x, and then the height of one of those rectangles as the function's value there, then the area of the rectangle is f of x times that change. So f of x delta x just represented the area of a rectangle. So we take that area right here, and we add an infinite number of them up, and it turns into the integral. So the summation sign, capital S, right, Greek capital S sigma, when you let the number of rectangles go to infinity, turns into this elongated, stretched out S, which we call the integral sign. Okay? That was the idea of Riemann sums. Add things up forever. Now, I want us to just make sure we pay a little bit of attention to, let me see what I want here. Actually, I think it's printed twice, right? It's actually the same thing printed twice, so. No, it's not on yours? Okay, it means I need to just delete one of those. It's all right. So the important thing was, look, our domain, on this function, our domain is represented by the ground here, right? Our interval, a to b, was our restriction on x. That was our domain restriction. And what we did was we picked a little infinitesimally small interval, right? Delta x. And then that was the width of our rectangle. And then the height we said was f of x here. The reason why I want you to see it is because we're about to go to a two-dimensional domain, and we need to understand, what each piece means also. So this is our little dx. What's the difference between dx and delta x? Okay, dx is what we use when we've gone to the infinitesimal, when we actually have let the limit go and take off to infinity. We get dx instead of delta x represents just general change in x. All right, so now, what if we are trying to find, instead of the area under a curve, the volume under a surface? So we can still use Riemann sums. So imagine, let me see, where's my surface? Here's the surface. My surface is like this parabola-looking thing, right? I wanted to go underneath that to the XY plane and find the volume of that little box right there. Everything underneath that. I want that volume, right? Well, to do it, what I could do is I could take a bunch of boxes, three-dimensional boxes, rectangular boxes, parallelepipeds is what they call them, and we could add up all the volumes, couldn't we? All right, and the more boxes we get, the better approximation. Let's see if that new memory I put in here does anything to speed that up. That's not bad, actually. That's pretty good. So the more we get, the better the approximation. Agreed? What the hell is this? So things might get crazy here because I have no idea what that controller does. Sometimes I copy and paste my own code, and I'll leave things in there from my previous code that don't do anything in this program. Oops. All right, well. And then we can change the function. That's kind of cool. That surface, part of it's above the XY plane, part of it's below. So when you're talking volume, it's going from the surface towards the XY plane, finding that volume. If it's below, it's counting it like that, right? Huh, look at this. The double integral here, the volume of this is 0. That happened with like sine and cosine too, right? Like if you look at sine function in 2D, and you look at it between 0 and 2 pi, if you find the area, or you integrate from 0 to 2 pi of sine, you get 0. That's because it counts the part above as positive and the part below as negative. Same thing we run into with double integrals. See if any of these are interesting. Yeah. So you get the idea, though. We have a Riemann sum, right? So let's take a look now at how we develop the Riemann sum. On the ground, our domain right now is a rectangle, right? So our restriction, does everyone understand we're looking at the ground here, two-dimensional space? Our x values are between two things, A and B. Our y values are between C and D. And then we're going to call this rectangle here R, this whole thing. And then what we do is we take this infinitesimally small rectangle, right? Or it's not infinitesimal yet. We're not going to take the limit. We're going to take a really, really small piece. We have a width, a length and a width. So that's our bottom of our box. And then the height of the box is the function's value at, I've been using this xi, yi, and no one has said anything about it, and I've been just kind of slipping past it as I've talked to you. No one has talked about what xi and yi mean, but, well, not in this case, unfortunately. xyi, and xi from the previous example is that when I'm trying to figure out how tall this is, what point do I plug into the function? Could I plug in this corner right here? This one? This one? This one? Well, xi, yi turns out to be any point in that little rectangle. It's quite an amazing fact that if you go back to this, right here, when I said you take the width and then the height is f of x, you can take the right side of the rectangle or the left side of the rectangle. It does not matter. Here, look. The volume right there is too much or not enough. Oh, wait, I don't like that one. Let's go right endpoint. Okay, what's the volume there? The true volume is there, right? Our rectangles, what I'm doing is I'm going to this end of the rectangle, I'm getting the height, and then I'm creating that rectangle. Going to the right of this rectangle, do you see I'm picking up the right side of the rectangle? That's too much volume, right? Now, if I pick up the left end, what happens? So this time I'm picking up the left end, going over, left end going over, left end going over. Left end over here is 0, so that's not enough, right? Well, at the end of the day, when you let the number of rectangles go to infinity, it turns out it doesn't matter if you pick the right or the left or any point in the middle. Any point in between. It does not matter, because what's happening is that the interval is getting smaller and approaching 0, so it doesn't matter which point you pick up. So we call it, instead of f of x, we call it f of xi or something like that, where it can be any point inside. And that's exactly what's happening with the two-dimensional picture, is that when we say pick some point to get this height, that point can be any point in here, which means any point in there. All right, so what's the volume of this box? Well, length times width times height, which is, right, this is our height, this is our length and width. And then if we want to figure out what, how to get a better approximation, we let the number of these things go to infinity, right? So to let them go to infinity means we need to take a double sum, let them, in one direction, let it go to infinity, number of them go to infinity, and then the other direction, same thing. You can look at it two ways. Make it smaller, infinitesimally small in both directions, or you can say, let the number of them go to infinity. Either way, it gives you the same thing. But this double sum turns into a double integral. And this f of x, I, yi thing here, that becomes just f of xy, and this delta x becomes dx, and the delta y becomes dy. And that's your notation for your double integral. Also, noticing that we have limits of integration. Our limits of integration AB and CD come from the restrictions on x and the restrictions on y. All right. So here's our general formula. The volume between f of x and the xy plane z equals 0 over a rectangular region. Notice the notation here, the rectangle R. The notation is the closed interval AB cross closed interval CD. That little cross here does not mean cross product. This is just the notation for a rectangle in two-dimensional space. You have the interval on the x-axis, the interval on the y-axis. You do a cross of those, and that gives you your rectangle. So the notation here, double integral over R of f of x, y, dA. Now look at what we use here, dA. dA, what do you think that stands for? Yeah, the infinitesimal area, right? Change in area or infinitesimal area. Well, what is the infinitesimal area? It's dy dx, isn't it? Now this may seem kind of like, who cares right now? It's kind of obvious from the geometry what's happening here. But as we move on in this class, all right, as we move on, give you kind of a long shot look at this. Here are all the formulas from chapter 13, okay, that where we're heading. So we've got integrals where it's d little s. We've got d little s there. Here it's dy, here it's dz. Here it's dr, but r is a vector. Here we've got ds again. We've got a dot product in here. Here it's d capital S. Here it's d capital S with a vector. They all mean something. They all have a geometric meaning. Right now, the dA on the outside of our integral represents basically a rectangular little box in its infinitesimal area, right? Just the way dx used to represent an infinitesimal width of a rectangle. So we want to kind of keep track of it all geometrically. It'll make things easier later if we understand that part of it. All right. Notice the way that we do this. If you have dy dx, then look at the order of your limits of integration on your integrals. You can look at it like an onion outside in. The outside variable is x. The limits here are the a and b were on the x-axis, right? That's our x and y restrictions. So then your next variable in is y, so your restrictions are c and d. If you switch this, then you have to switch these. Okay, so that's what I say here. If we're going to do this, try and compute this double integral right here, then what we do is we break it up. We do the inner integral first, and then after we do that, we come in and do the outer integral. But when we do this inner integral, it's just integration, right? Just integrate. But our function inside has x's and y's in it. So remember when we differentiated and we learned partial derivatives? We said treat the y like a constant or treat the x like a constant. Integration is the same thing. We have what's called partial integration. When we integrate and you have x and y in here, if you have dy here, then y is the variable. X is the constant. So when you integrate backwards, you have to treat x like it's constant, and the y is what you do all your methods on. That kind of makes sense? Y'all checked out a long time ago, right? So that's what all this says. All right, let's just get to this. So here's a function. Here it is. We have, it's on 0, 2, 0, 2. So here's 0, 2, 0, 2 on the ground, right? That's our domain. Our surface is somewhere, let's say, above it. We are trying to find what happens when you plug this curve into, or that into that surface. You get that little box up there. And we want to take everything below that box and throw it down to the ground and get a volume. Right? We want that volume. That's it. That's what we're getting with this computation. Now, the actual computation goes like this. Double integral. And then I think right now we should decide the order. So I'm going to go dy dx like this. And then we haven't answered that yet, but that's a great question. Does it matter, the order? The answer is going to be sometimes. Most of the time, it will matter. Okay, so the function in there was 16 minus x squared minus 2y squared. 16 minus x squared minus 2y squared. And what are my limits of integration? 0, 2, 0, 2. So integrate with respect So here's what I'm doing. I'm doing this first integral. When I say that, I'm doing, we'll call this the inner integral, okay? I want to do that first. So look at this three terms, right? 16, negative x squared, minus 2y squared. That's three terms. When you do integration, you can integrate term by term. What's the antiderivative of 16 antiderivative with respect to y, treating y like a variable? 16y, right? What's the antiderivative of negative x squared with respect to y? So we treat x like a constant. Negative x squared y. What's the antiderivative of negative 2y squared with respect to y? Negative 2/3 y cubed. Agreed? Now, we want to evaluate that. So this is the notation for integration, right? We go evaluate that from 0 to 2. Yes? Now, I'm going to add a little something in here. I did. Thank you. I'm going to just add something. I know it's 0 to 2, but I'm just going to throw in here, it's y equals 0 and y equals 2, right? I'm replacing my y with 0 and my y with 2. Why do you think that's kind of important here? I have an x in here, right? I don't want to make the mistake of plugging in 0 and 2 for x. Y was the variable. Y is the thing that's being replaced, okay? So let's plug that in. Now, we still have on the outside of this, what? The dx. So this equals integral 0 to 2. The inside there. Okay, remember how we do integrals? We start with 2, right? Plug it all in, bloop, and then we subtract what we get when we plug in 0. So plug in 2 for y, we get what? 32 minus 2x squared minus 16/3. Okay, that's what you get when you plug in 2. Now plug in 0. It's all gone, right? Plug in 0 for y. It's all gone, so minus nothing. And then dx. And then look, we're back in a Cal 1 problem now. Or no, Cal 2, sorry, wrong class. Well, Cal 1, shit, you probably may have seen this in Cal 1 because it's just a basic power rule integration. First calculus-based physics class I ever took. The professor was up there and they had some motion of something and it had a sine curve. It was a sine function. And then they were like, okay, if that's the motion, then here's the velocity. So it went all of a sudden, it went from sine to cosine, right? And I hadn't taken calculus 1 yet. And I'm like, what the? You know, like, what kind of algebra changes sine to cosine? You know, I'm like, I don't care, man. I just don't see it. I mean, it's just, you know what I'm saying? Like, how do you go from, if you don't know derivatives, so the moral of the story is, don't be careful when you take courses concurrently when they say you can do them at the same time, because a lot of times one of them will be ahead of the other and you need that other one. It's like, you know, I did learn it, but it was like a month or two too late. Okay, what's next? Integrate. Do I really have to do that? I don't have to do that, right? No, I don't. Nor will I. ... So that's just normal integration. What about this one? When I say ... that means you could figure out the rest, right? Okay. So y sine xy on 0, 2, 0y. I said that. 1, 2, 0 pi. God. My brain. Okay, that's the integral setup for that problem. Double integral. Again, keep track of things. I've got my pi and 0 on the inside. That goes with my y variable. Yes. Yes. On the previous one. Okay? Yeah, we're going to address that question. It's a great question, but we just let's wait and then we'll answer it. What's your instinct tell you? Maybe? Turns out if it's a rectangle that we're integrating over, so 0 to 2, 0 to 2 is a rectangle, right? If it's a rectangle, it doesn't matter which way you go. But see, where we're headed here is that, well, let's just see where we're headed, okay? Integrating over rectangle, you'll never see a problem like that on a test. It's too easy. We want to integrate over something more complicated. But we have to start somewhere, right? Okay, so we do this one. Let's do this inside one. So what's the antiderivative of this thing in here? Oh, shit, right? That's what you say? Antiderivative of that. I think I've said shit 3 times today and written it once. Must be time for the weekend. Must be time for a holiday or something. Yeah. Well, can we though? Can we switch it? Right? That would be a question. If I write the integral like this, would you agree this is a little tough to integrate? I mean, could you integrate that? What would you need? Integration by parts. You need integration by parts. But it could be done. I mean, that's like me asking you to integrate this. Isn't it? I mean, like the x is a constant. When I look at that, x is a constant. So could you integrate that? Well, I hope so. Right? But what if it was the other way around? What if it was that the x was the variable and the y was the constant? Then you wouldn't have to worry about integration by parts because you wouldn't have, see, here are variables in the sign and it's by itself, so we almost have to undo a product, don't we? Where if it's just the x variable, if the x is the variable, then the y is a number out there, and that's much easier to integrate. Do y'all see that? So why don't we say, and wonder to ourselves, can we switch the order? And we'll just say shit again just for fun, right? Shit. Okay, next is this theorem here, Fubini's theorem. If f is continuous, which means that it has to be well behaved, you can't have this thing that has these weird, we haven't really even, well, we did look at some functions that, remember the surfaces? In the very beginning, we were talking about domains, like some of those domains would be, the surface would be like, and all of a sudden it would dive down, and get crazy. If your function is continuous on the rectangle, well behaved, then the order does not matter. Okay? You can switch the order. But remember, if you switch the order of integration, you have to switch the limits of integration also. They have to switch orders too. So going back to this problem, I can redo this integral 0 to pi 1 to 2 y sine xy dx dy instead. And then do this one inside first. Anytime you're trying to integrate something with respect to a variable and you got that other one that's supposed to be a constant and you're getting confused as to how to do it, just take the problem and just replace the thing that's supposed to be constant with a constant and try and integrate it. It might be easier. Like, let me replace y with 2 here. 2 sine 2x. Could you integrate that? Okay, so the 2 could come out, right? So you don't have to worry about that. And then what's the antiderivative of sine 2x? Well, the antiderivative of sine would be negative cosine, but then you have to account for this, so you're going to have to scale it by a 1/2. So you're going to have 2 times, we said it was going to be negative cosine, and I scale it by a 1/2, and so it would be that. So it's just cosine 2x. Negative. That's what it would be, right? Take the derivative of that, and you should get that. Now, back here, I can ignore the y. I know that the antiderivative sine of something is negative cosine, but then I'm going to have to scale by what? 1 over y, because the y is like the 2 up there, right? And that 1 over y is going to come out here with this y, cancel it out. So we're going to have integral 0 to pi inside here. I'll even write down y times, it was negative 1 over y was what we had to scale by. And the negative came from the cosine, right? Antiderivative of a sine. Agree? And then we evaluate that from what to what? 1 to 2. What's 1 to 2? X is 1 to 2. And then dy is still on the outside. I'm going to cancel that out, those y's. So plug in 0 to pi. Let's see, if we plug in 2 for x, we get negative cosine 2y. And then we subtract from that negative cosine of what? Y? and that's dy. So I'm using fundamental theorem calculus, basically plugging in the values, subtracting the values, and can you integrate that with respect to y? I'll clean it up just a little bit. How about writing it this way? Cosine y minus cosine 2y dy. I think this one's easy enough that I can just take it all the way. Antiderivative cosine y, sine y, antiderivative of cosine 2y. I have to be able to scale that out. Do y'all agree with those antiderivatives? Yes, we took Cal 2 for a reason. And then 0 to pi. And you get nothing. For nothing. All for nothing. But geometrically, there's some weird stuff happening, because if you look at that surface, this is what it looks like. It's a pretty cool surface. All right? And we're looking at it over that rectangle, which is right here. And it turns out that when you take that surface and you look at that solid, take that surface back out of there, you can see that part of it was above and part of it was below. They cancel each other out. It's hard to tell that those are symmetric from our picture, meaning not symmetric. I'm not saying they're symmetric. It's hard to tell that it's equal as much volume on top as it is bottom, because it's not like cut right in half or something. But it turns out that whatever that volume is above and the volume below, that they are equal, they cancel. As long as the domain is a rectangle. Yep. And the function has to be nice, well behaved. Yep. So yeah, if f is continuous on R, and R is basically of this form, then you're guaranteed you can switch it. Okay.
So if you do get an integral equal to 0, and you still want to know the area under the curve, regardless of, you don't care about positive, negative, you just want to know, could you just change your bounds so that instead of going from, say, 0 to pi, you go from 0 to pi over 2, and then multiply the answer by 2?
Let me answer your question with something that will help us. Okay, look. When we have the sine function back in Cal 2 or whatever, if we were to do the integral sine x dx from 0 to 2 pi, we would get 0, right? What we could do is do the integral from 0 to pi of sine x dx, and that would just do this part, right? And that way we would know what that area is, and then we could always double it, right? But to be able to do that, we had to know where I hit, right? I had to know that value was pi. So I needed to know when the function was 0. In other words, I needed to know where the x-intercepts were. So if I go back to this function here, I actually need to know where my graph hits the xy plane. And you can see it looks like a curve, doesn't it? I would need to find the equation of that curve. And then my region on the ground would no longer look like this rectangle I just had. It would actually be something that looks like this, right? And we would just be wanting to integrate on this. And it's not a rectangle, right? The question is, can we do it? The answer is yes. This is what we call a type 1 region, and we're going to have a way of doing this. We would just have to be able to figure out what that function is. Once we have that function, we're off to the races. All right? Does that answer your question? Okay. But to find that curve, you'd have to set the function to 0. Set the function to 0, which is not as easy as it may look. All right. I'm going to skip that. That just says verify the theorem. So you're supposed to set that double integral up both ways. and show you get the same answer. So just verifying that the order doesn't matter. All right, a very special case with double integrals. If f of x equals g of x times h of y, that is, the function f that we're looking at is the product of a function of x only and a function of y only, then we have the following result. The double integral over the rectangle can be split up into two regular Cal 2 integrals. The first one using the a and b from x, and the first one integrating with respect to x, the second one going from c to d, and then just the y. So you can split double integrals into single integrals only if the double integral is a product of two functions of x and y separately. Now let me just show you with an example. Look at this one right here. Is my function of x and y a function of x times a completely different function of y? In other words, the x's and the y's aren't mixed together, right? The sine x is separated from the cosine y. Well, because of that, what I can do is I can take my double integral, what was it, 0 pi over 2? Yeah. 0 pi over 2, 0 pi over 2, sine x, cosine y, d, and it really even wouldn't matter what order that's in. But because this is separated completely from this, I can go integral 0 to pi over 2 of sine x dx times integral 0 to pi over 2 of cosine y dy. And do those two things separately, multiply the answers. But that's the only time you can do it. All right? That's right. It would work out exactly the same. Yep. It's just sometimes later it cuts down on time. Could you do it? Could you split this one up? No, right? Because the x and y are trapped together. So that could not be done that way. Properties of double integrals. These are all things that we've seen before with integrals. If you have a double integral of the sum of two functions, then you can split it into two double integrals. That works with addition or subtraction. If you have a constant in front of a function, you can pull the constant completely out of the double integral, all the way out. If you have some function is bigger than another function, then the double integral should be bigger than the double integral of the other one. So the volume under one function should be more than the volume of the other if one is on top of the other, right? That's what that's saying. Now, what about the volume between two surfaces? So given two surfaces, so we have an F and a G, two completely different surfaces. We have a rectangle. If I want to know the volume between them, so I have a surface on top, right? I have a surface on the bottom, and I want everything in between. Then isn't it just the volume of F? Right, that means volume of F, right? Double integral with that F, that means the volume under F completely, all the way, right? And then if I forget the minus sign for a second here, if I take the double integral of G, that's the volume under G. So if I take that G volume away from the F, you should have what's in between them. So that kind of makes sense. Same thing we had in Cal 1, right? The difference, the area between two functions, you subtract it. Uh-oh. Is that it? Is that the only note you have? That's it? Yeah, that's it. Okay. Let me just introduce what we're going to talk about. I meant like that's it. Like I couldn't believe that was the end of the notes. Let me see what our calendar says. How far behind are we? I'm sorry? 12.2 today? Why don't we come in on Friday? You want to come in on Friday? Okay, look, please do the sign-in sheet today. On June 30th, we did not sign in because it was the test day. So sign in on both columns, please. All right, for today and last class. There you go. Yeah, I do need that quiz. If you want that quiz grade, I will need y'all. Just kind of pass them somehow. Just be efficient and get them all to one place for me. So we're supposed to finish 12-2 today. What are we supposed to do next class? Say? What are we supposed to do next class? 12-3 and 12-4? Shit. All right, well look, let's do this because it has been a long week and you have suffered a little bit. Let me just show you what a general region is, and let me just show you where we're headed, okay? We know how to do an integral over that now, right? Theoretically, we do. But what if your region needs to be a little more interesting than just a rectangle? So the first region we have is what's called a type 1 region. And what it is that your x values are still stuck between two constants. So it's kind of like we still have the part of the rectangle, but instead of cutting it off with flat lines on top and bottom, we cut it off with two functions. And those two functions we can call g1 of x and g2 of x. Right? That's what a type 1 looks like. X's are between constants. That's what this says up here. My x's are between two constants, and my g functions, g1 is the one on the bottom, g2 is the one on the top. My y is stuck between two functions of x. Okay? See the difference between that and a rectangle? So when we have this, this is how you get it. First of all, we call the region, instead of R, we call it D. Okay, R was for like rectangle. D is going to be more like now domain. Okay? If we have a type 1 region, we have to do it this way. The constants are on the outside, A to B. A and B went with X, right? And then, instead of having constants here, we have functions. And so our functions are our limits of integration. And then our dy has to be on the inside. You are not allowed to switch order of integration when you have a type 1 region. You are forced to plug through it in the order that you have it. You have to. All right? Now, what the hell is this? Oh. Okay. I'm like, what the heck? Okay, so this is just a picture of it. What if I have a surface on top and a surface on bottom? I want to know the volume between them, but when you take their shadow down and you look at the region on the ground is a type 1 region. So see, this is type 1 on the ground. Three-dimensionally, your x's are trapped between two constants, and your y's, which are this axis, are trapped between two functions of x. Then your double integral would look like this. It's still subtraction, right? Double integral over d, f, and then take away g. This note is just more of a picture to see what's going on. Let me try and give you... No, I'm not going to do that. We won't do this. We'll do this next class. But look at this. Find the volume under this thing. What is that geometrically? That's a plane, right? That's a plane on the region bounded by these two curves. So if you plot those two curves, they're two parabolas. Here they are. Okay? The region between them is this in blue. Do you all see that this region is a type 1 region? Your x values are stuck between where? -1 and 1. your y values are stuck between these two parabolas. A top parabola, which we call G2, a bottom one, which is G1. So we will integrate this, find the volume, using that formula that we had just a second ago. And so that's the picture over there in three-dimensional space of the domain on the ground. Here's the surface, which is a plane. And then what we are doing is we're looking at the image of the plane up there, and we drop that solid down, and we have the surface right there. I mean, the solid right there. We want the volume of that solid. I mean, as you can see, we can really start to get some pretty complicated looking things and find volumes of pretty complicated things doing this. I think I'm exhausting you. I think I'm exhausted. Another one, same thing. Type 2 region, what's the difference? Not yet. Nope, that's not ever going to happen for us, unfortunately. Y is between two constants. And this time we're kind of like rotating our heads and we're saying now our x's are trapped this way. So if we do it, they're functions of y instead of functions of x.
Could you just take it a step farther and have x and y both be bounded by functions? So that, okay. You'd have some crazy looking region.
Well, it'll all depend because, you know, give me something crazy like this, right? Then I should be able to cut this up like that. I can call that a type, probably a type 1, or no, sorry, type 2. Looking at it like this. You know, I can cut it in different places, make each one of them certain types. And then once I've got it cut up in a certain type, I just do each one individually. So yeah, you can extend it. But there will be things that are much harder to do, like what if you have a region like this, and you want to do, your region is everything here. Right? What we'll do is we're going to convert everything to polar coordinates. And we're going to use a different coordinate system to do that. Or what if you're trying to find, if you have a sphere, and you're trying to look up here and maybe take a certain cut out of that sphere, some like pie slice out of that sphere, and just project that down to the origin like this, right? That pie slice down to the origin. And even better than that, why don't we cut it off here and like that, and just take the volume of that little piece in there. Very difficult to do with x, y, z cylindrical, Cartesian coordinates, so we'll convert to spherical coordinates. So we're gonna be doing integrals in Cartesian, which is what we're doing now. We're going to do integrals in cylindrical coordinates, which is basically polar in 3 dimensions, and then we're going to go to spherical coordinates. Those will be the 3 coordinate systems we use. One thing at a time, though. And let's start with 4th of July. Uh-oh. That's a sign. Let's get out of here.